This is Geometry Unit 4, Lesson 9 on rigid motion and congruence. Now, we looked in our last lesson about rigid motion, about what you start with is what you end with is with rigid motion. So, informally, two polygons are congruent if they have the same size and shape. What you start with is what you end with. We didn't change the size or shape, so the figures are the same with what you started with. Now, when you're talking about the congruence of two polygons, it's important to write the polygons so that corresponding or matching vertices are in the same order, so that the person reading it can understand what values match up with which values and how to get them to match. So, if I have quadrilateral RA and G and I want to match it up with this quadrilateral, I have to know what points correspond to what. So let's start with R. Well, we have R is between I and G here, and it's kind of the long sides of RI and G. All right, so what point would do that over here? Well, that would be point S. If I look at RI right here, here's point S, and it kind of goes up to the slanted one like so. So RI would correspond to S, I would correspond to T. Now, if I look at the next point, I to N, here's I to N is the slanted part, starting at the higher point. So that over here will go from T to O. So T would be O would be the next point. And then O would correspond to N here. So N then goes to G. So that means that O is going to go to P. So O to P. And then if we get our sides to match up, G goes to R. Well, G corresponded to P. So we would start at P and go to S and G to R. All right, so what's important about the notation is the points, the vertices that match up are in the same order. R corresponded to S, I corresponded to T, N corresponded to O, and G corresponded to P. So that's how you would match them up. If I flop this on top, the colors would all match. R to S, I to T, N to O, and G to P. Each one has to match up exactly to the vertices in exactly the same order. So that brings us to our more formal definition of congruent. Two figures are congruent if one is the image of the other under A. Well, what happens when they stay exactly the same? You are doing a rigid motion. So if you do a rigid motion, the figures will be congruent because what you start with is exactly what you end with. Remember, a rigid motion is a translation, a rotation, or a reflection. What you start with is what you end with, so the figures are congruent to its image. So, assuming they are congruent, describe a rigid motion that will take quadrilateral ABCD onto the other quadrilateral. Well, we want this to end up over here so that the sides and vertices all match up. So looking at the sides, AB would have to end up where? It would have to end up at QR. BC would have to be at RS. And then CD would have to be SP. And DA would have to be QP. So let's see if we can figure out a rigid motion that will do that. Well, it's kind of, we know it's got to turn somehow. If we turn it around like this, it's going to kind of go in the right direction. But that won't put it on top of it, so we probably have to slide it as well with the translation and then see what we end up with. So let's see what we can end up. We know we're going to probably have to do a rotation and a translation, and let's see what we can come up with when we do that. So if I look at my image down here, all right, for this one what we did is we started with this image right here. We started with a translation. So here's the figure. We did a translation along vector CP. So we went from here to here and slid it over to this dotted line. So this would look like this when we translate along this vector line right here, that vector. So we've translated this along here. Now, if we rotate this, we are rotating it around C. And what direction is that? We are rotating clockwise. And CW will be clockwise around P. And how long do we do that? Well, we kept going until BC prime corresponds to B double prime, C double prime. Or actually it would be the original line PQ to PQ. So we're pretending that we're turning this is turning like so, until it hits this segment right here. So that lines up. So that segment lines up. So this line goes up, or excuse me, this rotation goes up like this until this side right here hits QC. And then we want these points to line up. Well, isn't that a reflection? It's a reflection over QC, or QP, excuse me, over QP. If we flop this over this line right here, this will end up over here, and then everything will line up as we want. Now that's one possible way of doing it. There are more possible ways, but this is just one. So what you want to look at is how it rotates, how it slides, or how it flops. A good way of doing that is looking at if the size and shape changes, you know what it's going to be. It's going to be one of those three or a combination of those three. How can you get them to happen? You want to look, did it slide, did it rotate, and did it reflect? So those are the three possible ways that you could do this. So sometimes it may only be one, sometimes it may be a combination, and you want to see what you can do. Again, what's important about doing a rigid motion is for congruence. For a polygon, congruence is only possible if the vertices can be put into correspondence or matched so that all pair of corresponding sides are congruent and all pairs of corresponding angles are congruent. Because what you start with is what you end with. So the diagram that we just did, R had to correspond to A, Q is corresponding to B, C is corresponding to P, and S is corresponding to D. So that means that quadrilateral, the original one that we had, ABCD, would be congruent to quadrilateral in the same order, R, Q, P, S. So those are congruent. So when you are given a congruent statement, you should immediately be able to pick out what parts are congruent. Do yourself a little sketch if you need to. If we had triangle dog is congruent to triangle cat, you want to draw two triangles that are exactly the same. So triangle dog, whoops, let me do that as a solid line. Here's triangle dog, would be congruent to triangle cat. We're going to draw two identical triangles and label them exactly the same way. So I'm going to say D, O, G, like that. So if I went around clockwise like that, I also have to go around clockwise C, A, T, starting at the same place. So D corresponds to C, O corresponds to A, G corresponds to T. So knowing that, now that we have that, we can automatically say which angles are congruent. Angle D should correspond to what angle in the other triangle? Well, angle C. Angle D is congruent to angle C. Angle O should be congruent to angle A, right there. And angle G should be congruent to angle T. So all of those angles are congruent because of the way the congruence is given. Now, the sides are also congruent. The side DO should be congruent to what side? Here's DO. That should be congruent to CA. It's in exactly the same place. It has exactly the same corresponding vertices. So DO is congruent to CA. There's one pair. OG, the next side. Here's OG. In the same place, AT. OG is congruent to AT. And then the third side, GD, should be congruent to TC. It is congruent to TC. Now look at your values here. D is to C, O is to A, G is to T. There's your three angle vertices. DO, CA, exactly. OG, AT, and DG, CT, or however I said them, the same order. Each vertex is named exactly the same way. Each of the vertices will correspond to each of the segment. Now let's see if we can describe a ridge motion that will take triangle RAT onto the other triangle. So here's triangle RAT. What is triangle RAT doing to get to OCW? Remember, A corresponds to O, R is to C, and T is to W. Because notice right here, that looks like a right angle. It might be. Well, this one looks like a right angle there. So what transformation are we doing to get this from here? Well, it's going to be a translation. So we have to know how far to translate. So we have to translate something. So we want to translate how far? Well, we want to go over this far and up that far to get over there. So each point is in the same place. Well, why don't we translate along the vector RC? Here's RC right here. If I connect R to C, we do it a different color. If I go from R to C, like so, I went over this distance and up here. If I go over that distance in each one, that same distance, we want to translate along vector RC. We go that distance. So if we do the same thing for each of the other points, we want to go the same distance like that. Each point will go over and up that same distance. So our vector would be RC. That's a translation. All it did is slide. It didn't change, it didn't rotate, it didn't, the orientation stayed the same, so we knew it just slid. Now let's look at the second one here. We have triangle RAT, and we want to end up over here. So again, R ends up at F, T ends up at L, and A ends up at Y. All right, now notice the orientation of these. The orientation is flopped the opposite way. So what kind of transformation is this? Well, probably it's going to be reflection some kind, but what are we reflecting over? We want to probably reflect over a line, but where is the line going to be? Well, I would say if we reflect over, we know it's going to be about here. There's our line of reflection. Now, how are we going to describe where that is? Well, we could reflect over the perpendicular bisector of TL. Of the segment, and when we say TL, we are saying the segment that connects T to L. So if I go connect from T to L right here, isn't that halfway across? Yeah. So there we go. That's perpendicular, and it bisects the segment here. Now, if you connect each of these points, A to Y and R to F, each of those will have that as a perpendicular bisector. Now, is that the only way you could do it? No. You could also say, why don't we translate along the vector RF? So you would start at R and you would end up at F. So if you did that, let me do it in a different color. You went from here over to here. All right, so that would actually create this triangle out here. All right, F would end up over here, or T would end up over here, A would end up over here, and then how would we get it over to line up with the points? Well, T would get to L by reflecting it over AF. So you could do either of those transformations with your motions and it would still work. So you could slide this along here to get here and then flop it over AF, or FY, I'm sorry, not AF. FY. Reflect it over FY and it would line up. So it's not always just going to be one motion. There's more than one way you could do that by combining your different motions. All right, let's try letter C. Well, it looks like this is flopped onto the side, so probably want to do a rotation. Now, if we want this triangle to look like this triangle, we probably have to rotate this way, and probably 90 degrees, which would put A out prime out here, like so. So we would probably want to rotate 90 degrees counterclockwise around R, and then that'll put it like this, and then we just have to translate along vector RP. So we want to start at R and then slide it over until R corresponds to P. And we could do that. Now, could we do that in reverse? What if we translate it first and then rotate? Yeah, you could. That would be another way of doing it. All right.